My name is Sophia Isaac, and this is my experiment 3, macroscopic view of DC and RC circuits. So to start, this is a table of contents, as this is a general overview of what we're going to be talking about today, starting with the introduction. So the purpose of this experiment is to predict the behavior of circuits with resistance and panels, examine the behavior of ohmic resistors and capacitors, and then measure the actual values and compare. And this is all under the assumption that wire resistance and ammeter resistance is negligible. And a preview of the final results that I got was that I got the same RC values for both the measured and calculated values. So some background information. First of all, it's Ohm's law, which basically tells you that voltage is proportional to current, and it's represented by this equation V equals I times R. And then both the node rule and the loop rule, which we're going to be using for the circuits, which is that the sum of the currents in equals the sum of the currents out, as well as the total changes in potential is going to be equal to 0, as well as capacitance, which is the ability to store electric charge, which is Q equals CV, and then conservation of energy, which is that energy is always conserved. It's neither created nor destroyed. So to start with the procedure, the system is a circuit, the surroundings are everything else, and initial conditions when it's off, the charge is 0. So what we're going to do first is, based on this current, we're going to predict the currents of, based on this circuit, we're going to predict the currents of I1 and I2 from this. And then we're going to recreate this in CCK, which is the software that we're going to be using for the circuits. And then we're going to compare the values. So the results for this part was the predicted current that I got based on the equation that we talked about before from Ohm's law is that I equals 0.02 amps, and the current that I got from CCK with the reversed ammeter was the same value, 0.02 amps. So comparing both predicted and measured values, they are equal. And then when we remove the ammeter and replace it with a voltmeter, we get that the potential difference is 3 volts, but the current is equal to 0 amps, and that's because it's an open circuit. So after taking this as a baseline, when we close the circuit and remove the voltmeter, but then we use the voltmeter to measure the potential difference by touching the two leads to the points that we want to measure across the entire circuit from A to H. And we have to record the potential difference across those segments as well as record the current. So these are the values that I got for all the different segments, and when we add all those potential differences together to find the total potential difference, we're going to be equal to 0, which was expected since that's basically the loop rule. And the current is going to stay the same at 0.02 amps. So for other results, this is the graph that I ended up doing from the potential difference across the points. And the questions are, when you touch a voltmeter, you alter the circuit, why doesn't it change? And that's because the resistance of the voltmeter is so high that no current passes through, so the circuit is essentially unchanged, and the ammeter reading remains the same. And if you replace the voltmeter with an ammeter in parallel with a 100 ohms resistor, what happens and why? And the current changes to 0.06A, and that's because less current goes into contact with the resistor and ammeter resistance decreases. And then we have to calculate for the resistor for all these values. I got that it was 48 ohms, 102 ohms, and then 0 and 0 for the wire and the ammeter. Then part 3, for the RC circuits, we have to connect the battery to the 10 ohm bulb and capacitor in series. Observe the light. What happens to the light? So what happens to the light is that it turns very bright, and then it turns off gradually and starts to dim out until it completely turns off. And if we disconnect the battery and connect the capacitor, what happens to the light? Basically the same results. It turns really bright and then starts dimming. And then we have to disconnect the capacitor and discharge it through the right click menu. When we first connected the battery to the capacitor, and then it was charging. So what happens to the current? The current is at its peak and then it gradually decreases, so essentially a similar behavior to the light bulb. And then when we remove the battery and the capacitor begins discharging, what happens to the current? It's basically the same as the previous circuit. So we repeat this and for the 20 ohm bulb as well, and we measure the time it takes to charge and discharge. So for the 10 ohm bulb, it was 10.2 seconds to charge and 12.5 to discharge, and for the 20, it was 18.7 seconds to charge and 23.2 seconds to discharge. And then setting up a circuit in the CKK with a 9 volt battery, a 200 mF capacitor, and a 3 ohm light bulb, and we have to measure it for 20 seconds. And that's basically what I did, and then I plotted this value for the ln of delta V over delta V0 in order to get the value for the RC. And after getting this plot, we basically used this to solve for the RC value, and we get that the RC is 5.99 seconds, while the calculator RC that we expected is R times the capacitance, which is 6 seconds, which is very similar. It's essentially the same number. So for the conclusion, possible sources of error can be error due to rounding or math, or error when measuring times and slowness based on my part, and similarities, essentially the same RC values were measured and calculated for both, so those ended up being the same. And then what if we're doing this in real life? What's different about the real ammeter? How would it affect it? So it would be different because a virtual ammeter had no resistance, but the real ones do. So the values for the current would be lower. And then what if we were doing this in real life and used a real battery to charge the capacitor? How would it reach full charge, and would it happen in real life? So it would reach full charge in a slower time because in real life batteries do have resistance, and virtually in the ideal situation they don't have resistance, so it basically charges right away. And so essentially in real life it would just charge at its peak, but it would just take a little bit more time.